Graph the function f of x equals 2 secant x minus pi plus 1. All right. So whenever we graph a secant or a cosecant, what we need to do is we need to graph its reciprocal function as a rough draft, as a guiding point. So I'm going to, in purple, draw a rough draft of f of x equals 2 that was a close one. Cosine, that was a close one. I didn't do it though. X minus pi plus 1. Don't jump in the comments and tell me I make a mistake. You guys like to do that, which is fine. I deserve it. But I'm going to draw that as a rough draft. So lots going on. The period is still 2 pi, but I'm going to shift it to the right pi, so it's going to shift over there. I'm going to have a midline of plus 1, so that's right here. It's a cosine with a amplitude of 2. So it's going to start up here and then still have a regular period of 2 pi, which means it's going to completely repeat all the way over here at negative pi, which means it's going to bottom out down here at 0. Although, hold on, I think I went way too far on that one. I did. It's going to bottom out, since the amplitude's 2, it's going to bottom out at negative 1. Okay, which means it's going to come back up, bottom out there, come back up, bottom out there. And there you have it. So inflection points are going to happen directly in between. So U, U. And I'm in purple going to draw a dashed line just as a guide as to what this is going to look like. Now this isn't even in the graph. We're just going to pretend that purple is imaginary. Okay, purple doesn't exist. Okay, it has nothing to do with our final graph. What we need to do and remember is anytime you have an inflection point, right? Anytime you cross your midline for your rough draft, that is going to be a vertical asymptote for the actual graph. So you cross the midline there, you cross the midline here, you cross the midline there, and you cross the midline there in blue. Now we are going to have, and what secant generally looks like is you have like a series of parabolas, looks like that, series of parabolas, looks like that. And so what we're going to do is we're going to use the maximum values and minimum values of the rough draft as our starting point for the actual graph. All right, so starting at the middle here, you're basically going to go down and look like a parabola that's concave down. Don't have a lot of space here, but you're going to be concave up like that. You're going to be concave up like that. And don't have a lot of space, but concave down right there. Concave down right there. What I have in red is my actual graph. That is my actual graph. The purple was just my rough draft, my guide, my blueprint. Okay? Vertical asymptotes in blue, easy peasy. State the domain of the function. Oh. Okay. Well, I didn't do a good job saying that. I mean, the domain is like everything except for the vertical asymptotes. Am I only focusing on negative pi over 2, 2 pi? I guess I am. Maybe that's what I meant to do when I meant that problem. So let me reword this. State the domain of the function on the picture that we see, negative 2 pi rather, to 2 pi. So if we're only focusing on just this section right here, just that area right there, wherever the red touches is my domain. So it starts out at negative 2 pi. And then hits a vertical asymptote at negative 3 pi over 2, not including. Union. Starts back up at negative 3 pi over 2, not including. And goes all the way to negative pi over 2, not including. Union. Picks back up at the same exact spot. Goes all the way to regular pi over 2, not including. Union. Picks back up at the same spot, pi over 2. goes all the way to 3 pi over 2, not including, union, and then starts back up at 3 pi over 2, the same spot, hits 2 pi, which we're going to keep. That's going to be the domain for this picture. What are the vertical asymptotes? There's 4 of them. Okay, x equals negative 3 pi over 2, x equals negative pi over 2, x equals regular pi over 2, and x equals 3 pi over 2. Lots happening in this problem, but we did it.